general relativity predicts black holes. From the
Yeah,
theory, it was like black holes had to exist. Whereas something like a wormhole, it's hypothetical, but
yeah.
it doesn't have to exist. So like, what's the difference between the two when you kind of look at them as different possible solutions?
Yeah, well, the wormholes are even more stranger than black holes. But in the case of black holes, I mean, the solutions look strange because you would have this thing where light doesn't escape. So people were skeptical about whether this would exist. But then what people proved that is if you get enough mass in a small enough region, then the gravity of that mass will force it to compress and collapse on itself, and you end up with a black hole. There's nothing you can do
Mm.
about it. That's what happens. And then people would say that's never going to happen. But then people studying astrophysics realize that that will happen with very massive stars. The sun will never be a black hole. The sun is not a very large star, but
Mm.
stars are about 20 or 30 times the mass of the sun, and there's millions of those stars. Eventually, when they die, because they become the fuel inside the star eventually finishes. They end up with all the fuel finished, and then they start cooling down. And when they cool down, gravity wins over the pressure, because normally a star is a balance of two forces, right?
Mm.
Gravity wants to collapse the star, but the pressure of the hot gases in the star wants to expand it. And then they achieve an equilibrium. But that's because they're hot. Once the fuel runs out and they become colder, then they start compressing. The process can actually be very violent, because this compression, when they switch off, the compression happens really quickly. And it's so violent that actually the star explodes. You call that a supernova. But,
Mm.
but when the star explodes, not all the star explodes. The outer layers go away, but the core of the star remains. And that core of the star is now colder than it should be, and it keeps compressing and collapsing. And the theory tells you that it will just collapse all the way to a single point, and you end up with a black hole. And that's inevitable. We don't know of any law of physics that can prevent that. And we have evidence that this actually exists in nature. We've seen the evidence that black holes exist. So that's black holes. Wormholes are different. Wormholes are essentially like a tunnel in space. That is like a shortcut. So you can have a flat surface, for example, and then you have a sort of a tube that connects it to a lower surface, and then you go through the tube to the other side. So it's like the handle on a cup as well. So you can go through the handle to the
Mm.
other side. So wormholes are allowed. The mathematics of general relativity allows wormholes. You can have the solution in the sense that you can write the mathematical equation for a wormhole. But first of all, nobody knows how they would form.
Mm.
It's different from black holes. Black holes, we do know how they form, and not only that, we know that they're inevitable. But with wormholes, nobody knows how they would form, because you have to make a hole here that ends up there, and nobody knows how to do
Yeah.
that. We don't know how to make a hole in space-time that will, you make a hole here and comes out somewhere else. We have no mechanism for that. In the theory, there's no mechanism for that. So we know how to make them, and not naturally or not artificially. But even worse, because when you put them in the theory, it turns out that these wormholes are always unstable. Even if you had one,
Mm.
it would collapse on itself and disappear very quickly. So the theory allows them to exist, but we don't know how they could form, and they are unstable. And if you wanted to have a stable wormhole, then the theory tells you that you need anti-gravity to keep it open, because it has a tendency to collapse. And if you want to keep it open, you need an anti-gravitational force, sort of repulsive gravity,
Mm.
which, as far as we know, doesn't exist. So that's because that's the reason why they're theoretical. And wormholes are like also the warp drive. I think we're going to talk about the warp drive in a minute, but the wormhole solutions and the warp drive solutions are not true solutions of the Einstein equations. They're cheating. That's why I never
Yeah.
like to call the warp drive a true solution. It's cheating in the following sense. Normally, a solution is you have this distribution of mass and energy, and you're trying to find out what is the geometry of space and time that is produced by that. So you solve the equations in a very complicated way to find the curvature of space coming from that distribution of mass and energy, which might be a star or something. The wormhole solutions and the warp drive are the other way around. You say, I like
Right.
this geometry. I want this geometry. It's very nice. It's very pretty geometry. It's interesting. What is the distribution of matter that would produce this geometry? So you go the other way. And that's easy. It's very easy. You basically just plug in the equations and read it out. You don't have to solve anything. and it comes out. And when it comes out, what you find is that usually what comes out is nonsensical. You get a nonsensical distribution of matter. You have negative distributions of energy. You have things that must move faster than light, and that doesn't make sense. So you get something that's nonsensical. And so, in that sense, they're not true solutions. They're because if those were solutions, then anything would be a solution. Any geometry that you come up with would be
Yeah.
a solution. So in that sense, I don't like to call them solutions.
Mm.
I prefer to call them designer spacetimes. You
Designer
design the
space
geometry
times.
of the spacetime the way you like it, and then you say, well, but I would need anti-gravity to produce that, and I don't have any anti-gravity, so bummer. But
I gotta call
but
this video "Designer Space Times." I
well,
love
yeah,
it.
that's what they are, and so it happens with wormholes, and it happens with
Mm.
the warp drive. In that sense, they're not. They are hypothetical because of that. We have no idea how to produce them. You would require matter densities that make no sense. For example, you would require typically negative energy
Mm.
or anti-gravity, and we don't know anything in nature that has anti-gravity. So that makes them unlikely, if not actually forbidden. So yeah, it's not that they're forbidden. The theory doesn't forbid these geometries, but they seem unlikely because they require something
Yeah.
we've never seen, right?
I think that's a really great point that people don't get, and I definitely didn't get that point
Yeah,
myself, that we're working backwards, that's what the
exactly.
difference is, and that, like,
Yeah,
it's fine when you can take something and you can go, this physically exists, like say like a star, and
yeah,
this is what we have, what will happen with
exactly,
that, what will be the result, versus going like, this is the result we want, what do we need to create it?
exactly.
And
Yeah,
that's a
so you're
great
going
way to
backward.
think about it. It's like, well, what do we need to create it? And that's where all the problems come in.
Exactly,
So
because usually
we
you
should
get something
probably
weird.
come into that.
Yeah,
So I recently made a video, and I'm just
yeah,
going to tell you this because I think it's funny. So I recently made a video where I explained the original background of warp drive in Star
yeah.
Trek as described in the TNG
And the technical
technical
manual.
manual.
Yeah,
Yes. And I described it as subspace. Now,
yeah.
nearly 300,000 people watched that video, and at least 50% of them told me I was wrong. And they very kindly explained to me that warp drive is, in fact, when you contract space in front of the ship and expand it behind the ship. And don't I
Ex-
know, it's called the Alcubierre Drive. Did you ever imagine that the fandom would basically change the definition of warp drive because of your paper?
I didn't. I didn't. I was really surprised. I mean, when I wrote the paper, I was 27 or something, and I was a PhD student, and I just thought this is interesting and this is funny. And my point was to try to show that the fact that nothing can travel faster than the speed of light in relativity has to be qualified in the sense that you cannot travel locally faster than light, but globally you can deform the geometry in such a way that you might be able to go faster than light in this region, not actually faster than light in there, because light would still beat you, but in this region you can go faster than light would go in another region because of the geometry and
Mm.
the formation of space. So that was my idea, and I thought it would be interesting for the physicists, but I never thought it would explode into science fiction.
I'm pretty sure that, like, even in the show, they started to retcon it a little bit, and they started
Exactly.
explaining things. Like, I don't know if you noticed, when Enterprise came out, they started describing it as a gravimetric field displacement. I was like, this
Yeah,
is
they
sounding a
tried
bit
to.
familiar.
Yeah, because subspace doesn't make any sense. It doesn't exist as far as we know.
Yeah.
But yeah, they're trying to retrofit
So there you
it.
go. Whether you like it or not.
Yeah, it's funny because a lot of people actually think that I actually designed a spaceship, and which I
Yeah.
never did, of course, right? Or designed an engine. So they tell me, how does your engine work, or what sort of fuel it uses? I have no idea. I mean, I never designed an engine.
Yeah. So what does your solution, not solution, your designer spacetime actually
Exactly.
say? What is your designer spacetime?
Yeah, I basically just presented a plausible geometry of space-time, and the idea came from the expansion of the universe. Initially, I was actually inspired by something we call inflation, but it doesn't really matter too much. People have probably heard that the universe is expanding. We've known that for 100 years
Mm.
now. The universe is expanding. This expansion of the universe, people also don't understand it really well when you talk about them in science communication, because the name is not a good name. We call it the Big Bang theory.
Mm.
And Big Bang is not a good name. It actually it came out as a joke, or even worse, it was trying
It was
to put it down to show that it was something
yeah,
nonsensical.
was
Right?
it Fred Hoyle?
What was Fred Hoyle who was
Yeah.
saying that people believe the universe started in some sort of Big Bang, and the name caught on. But the
It
name is not a good
sticks.
name because the Big Bang
Yeah.
didn't happen somewhere. It happened everywhere. There's no central point
Mm.
of the explosion. It's not an explosion in the conventional sense. It's actually space stretching. We know that initially, in the very far past, 14 billion years ago, the universe was very dense and very hot. Everything in the universe was with the huge densities, higher than the density inside an atomic nuclei, and extremely hot. And from then, it started cooling down and stretching. Space stretches. That's the expansion of the universe, is space
Mm.
stretching. If you have two galaxies, they're far away from each other, they're essentially not moving too much. I mean, yeah, galaxies move, but they don't move too much, and they don't move too fast. They move very slowly. But space in between them is growing. It is stretching, and this is the expansion of the universe. So, and it gives you a law, which is Hubble's law, which Hubble discovered it, and it also comes out directly from general relativity, the same law. It tells you that the speed at which galaxies separate is directly proportional to the distance between them. So we have two galaxies that are at, say, at a given distance, they move away at some speed, but if they're 10 times as far away, then they move away 10 times as fast. And if they're 1,000
Okay.
times further away, they will move away from each other 1,000 times faster. So then this gives you immediately a question. If you have two galaxies that are very, very, very far away, can they move away from each other faster than the speed of light? And the answer is yes, that happens. We actually call that the cosmological horizon. And
Mm.
the next question is, that doesn't violate relativity? And the answer is no, it doesn't violate relativity. It's actually a consequence of general relativity because the galaxies are not actually moving too much. It's space between them that is stretching. And space can stretch faster than light if it's sufficiently large, and that's okay, that's no problem. So that was the inspiration. I thought, if this can happen at huge distances between galaxies that are very, very far away, and we know it does happen, then how about we make it happen in a very small region behind me? Okay. Instead of expanding the whole universe, I can just expand space behind my chair. And if I could do that, then this stretching of space behind my chair will move it, would move me toward the next wall, but it wouldn't actually, I wouldn't be moving. It would be space stretching. And then I thought, okay, that's okay because it would move me far away from that wall, but it doesn't really help me to get to where I want to go. So because I only stretch it here, I didn't do anything in front. So what I can do is compress it in front, which is like a stretching in the opposite time direction. It's just like a reflection, right? So if I can expand space, I can also compress it. So I can compress space in front and expand it behind me, and that would move me away from whatever's behind me, move me closer to whatever's in front of me, and I wouldn't actually be moving. And that, if that can be done, it can be done faster than light, because we know that happens in the whole universe. So that's the basic idea. And the next was math. The next thing was to do it,
Yeah.
to put it in math, to design, to write down the geometry, the mathematical expression for this geometry that has this expansion and this contraction in front. I call it a warp bubble because it's a bubble of space-time in which you have an expansion behind you, a contraction in front, but in the middle, inside the bubble, nothing is happening. So you
Mm.
sit very comfortably inside the bubble. And then I came up with a mathematical expression for this geometry, and that's what I published in my original paper. The mathematical expression for this geometry. I said, in principle, that this could be done faster than light. It's not, doesn't violate any laws. It's allowed by general relativity. I went a bit further because as I said, this is a designer's space-time. I had the geometry that I wanted in mathematically expressed, but then I plugged it into the Einstein field equations and went backwards and said, okay, what sort of distribution of matter and energy I need to produce that? And the first thing you realize is you need negative energy. This
Mm.
requires you to have negative energy. And negative energy is a no-no in general relativity.
Yeah.
Everything we know has positive energy. Negative energy would produce a kind of anti-gravity. But we've never seen negative energy in the universe. There's no field that we know of that can produce negative energy. So that when you see that, you say, oh, well, that's bad. Okay, we need negative energy. That's a problem. Maybe this is not possible. But then I finished my paper saying, oh, maybe it's not possible, but at least this shows that in principle, it's not forbidden. So we
Yeah.
need to probably clarify it. And then I just went to a side point that something we've known for almost 70 years, that in quantum physics, in quantum mechanics, there's some times in which you can have very, very small regions of space with very, very tiny amounts of negative energy. It's called the Casimir effect.
Yeah.
And say, well, the Casimir effect exists, I said. This shows that you can sometimes have a little bit, tiny bit of negative energy in a small region of space. Maybe we could make this bigger, we could make it work. And that's a paper. That's
Yeah.
the paper. Because I never talked about spaceships. I mean, I used an example with spaceship. I didn't design a spaceship. I didn't design an
Yeah.
engine. Nothing. I just talked about the geometry of space.
Yeah. I think that's the thing. It's like, because it's the geometry, and it's really cool and it's really exciting, but then it does bear
Yeah,
the question of like, but how do you make it? And that's the
exactly.
part that people can't figure out. Because it's like,
No,
so you're in
we
your
can't
ship,
make it.
you're in your little bit of space, and then it's like, okay, now I just need to create a whole bunch of negative energy there, and a whole
And
bunch of
back
positive energy there, and
and
stuff happens.
exactly, yeah, and you need to put it in the right place, and then there's other couple of problems. One that I didn't realize immediately, but was an obvious problem. If this bubble is traveling faster than light, then you're sitting in a spaceship inside the bubble, and you need to put some of your negative energy in front of the bubble, uh, and it's traveling faster than light. Then you cannot reach the front of the bubble from inside the bubble. You send a laser beam towards the front of the bubble, it gets stuck midway through the wall of the bubble. It doesn't get all the way in,
Oh.
because if it could, it would be
Mhm.
traveling faster than light outside, and it can't. So it gets stuck in the middle of the bubble, which means you cannot reach the front of the bubble, which means you cannot put there the necessary negative energy, even if you had it, which is a problem. We call that the horizon problem, and that's a problem.
Right.
And the other problem is the amount of negative energy. I mean, even if you
Mm.
said, okay, I found negative energy, now I want to do it, you need ridiculously huge amounts of negative energy. I mean, even if you're very conservative and you say, I want a bubble in which just you can fit something the size of a commercial airplane, and it's going just at the speed of light, not even faster, but precisely at the speed of light. And I think that the bubble walls are about at 10% of the whole volume of the bubble. And you do a calculation, it turns out you need about 60 times the mass of Jupiter turned into negative energy just for that one tiny bubble. So the amount of energy becomes completely ridiculous.
Yeah. So
So-
that's interesting, right? Because whenever I talk about this, what the things that the arguments people will always come back to me with is go like, oh, well, what about the Casimir effect? And it's like,
yeah,
cool, come back to me when you figured out how to scale that up. And then
exactly.
the second thing is like, is the energy conditions, because I think that there is this general thing that we struggle with just as people is scale.
Yeah.
Like, it's really hard to
Yeah.
understand when we're talking about like really teeny tiny things and really, really massive things. Mass energy is mass energy.
Exactly.
You're going to need that amount. Like, it doesn't
Exactly.
matter whether you get it from fusion or whether you get it from like wherever you get it from, that is the amount of energy that you need.
Exactly.
And there's limited resources in the universe. Like, I know
Yeah,
we have a
exactly.
massive universe, but like, if you want to create a warp bubble to get out of the solar system and you use up Jupiter
And
to do it,
to do it once, exactly.
that's a one way. Exactly, that's one journey. It's like
Exactly.
just out harvesting solar systems.
Exactly.
Um,
The amount of it. And the problem with the reason that happens is that space-time, it's a very difficult medium to curve. It's very
Mm.
rigid in the sense that you
Yeah.
need huge amounts of energy to produce very tiny curvatures. The Earth is a big planet beneath us that produces the gravity that keeps us stuck to the ground. And when you see how much it has deformed space-time, the actual curvature of space-time around the Earth is 1 part in a billion
Wow.
away from flat. It's just 1 part in a
Yeah.
billion away from flat. And that's the Earth. And the sun, which is much bigger, the curvature space around the sun is 1 part in a million away from flat.
Oh my God.
So it's the
Wow.
curvature is tiny.
I've never thought about it from that perspective, but it is fascinating because I think when we think about science fiction, and not just warp drive or wormholes or anything like that, but even just simply like artificial gravity, because as you're saying, like, in order for it to work, you need anti-gravity, and it's
Yeah.
the same thing for like all of these sci-fi fantasy ideas of people just walking around in spaceships. It's like you need some way to create
This
what the Earth
gravitational field.
creates, and
Exactly.
like The Earth is
And
really
yeah,
big.
and we have no idea how to do that. I mean, that's one of the
Yeah.
reasons I like the expanse, because in the expanse they don't have
Mm,
artificial gravity. All the gravity is
yeah.
acceleration based.
Yeah.
The rockets
It's
are
so
firing
good.
all the time, and that
Yeah.
acceleration from the rockets
And
keeps
then the
you.
flip.
And then they flip. Yeah, exactly.
Like, yeah, I mean, but this is the thing, like, there's really cool things like that that we can do, as you said, like in the expanse and these ways. But when you are talking about actually trying to change the curvature of space-time or create these designer spacetimes, it's
And wormholes is similar. Yeah, exactly. To produce wormholes is the same amount, is also a ridiculously huge amounts of negative energy to produce a wormhole. And that in the case is even worse, because we don't even know how to make a hole here that ends up there. That you have to change what we call the topology of space, making holes here, and we have no idea how to do that.
so. I do have a question, and I don't know if you'll have
Yeah.
the answer for this. But when you do think about that concept of the contraction and the expansion, what happens when the warp bubble gets turned off?
It's a very good question. Yeah. Well, I never thought about that myself. I always thought it's going to be on, and whatever happens when they turn it off, I have no idea. There's a couple of interesting things about that people have worked out. One thing, it's old. It's more than 20 years old. That people thought, okay, when the warp, this bubble is moving faster than light, it's catching up any radiation that is in front of you, even if it's moving
Mm,
away from you, because you're moving faster, so it catches up with it, and all that radiation accumulates in the front of the bubble. And when you turn it off, all that radiation just goes away, and it can be a huge amount of radiation. So it would be
yeah.
extremely dangerous to anyone to be in front of the bubble when it turns off. It would be surrounded by radiation that it just picked up everywhere. So it would be extremely dangerous. But the other nice thing that people did a couple of years ago, a group in the UK, was they said, okay, we cannot simulate numerically as what I do with black holes. We cannot simulate numerically the warp drive, and the reason we cannot do that is because we don't know what kind of matter. We don't have a model
Yeah.
for the matter. We know you would need negative energy, but that's not enough. We would need the equations for this negative energy, how this negative energy behaves. We would need the equations to plug them back into the simulation. And we don't have that, so we don't know what to do with that. But they said, okay, let's forget about that. We don't know how to do that. Let's assume that it's moving and suddenly they turn it off. Once they turn it off, then we don't need the negative energy because it's switched off. So we start with this bubble of this warp bubble, but it switches off. There's no negative energy anymore. So what happens with the bubble when the negative energy goes
Yeah.
away? And that we can do, because if there's no energy, we can solve the equations. So they did this, and then they said, what happens to the bubble? And it turns out that the bubble disintegrates. It goes back to flat space, but it does it in a very violent way. And this thing produces gravitational waves, these perturbations
Mm,
of gravity that I mentioned before that travel at the speed of light. And those gravitational waves turn out to be very strong. So you should be able to see these. If somebody's traveling in one of these warp bubbles in a region of the galaxy and suddenly they turn it off, then these gravitational waves coming out of this thing we should be able to detect them with the detectors we have today. And that was very cool. I really thought that's a really cool paper.
yeah. That's people kept asking me that question when I did something when I did a video on warp recently, and people kept saying that. They were like, oh, could we detect them? If you like,
if, they,
surely there'd be some, like,
if they
surely we'd
switch
see
off like that,
something.
then
And
we
I
should
didn't
be
I
able to
didn't
detect them.
register that.
Yeah,
So
yeah,
that's really cool. So
because
there
it
you
would
go.
produce
Everyone, I was
gravitational
wrong.
waves.
I'm sorry. You totally can. Gravitational waves, you can do it.
Yeah, exactly. We can detect gravitational waves. Yeah.
But what I do wonder about that though is the warp bubble goes down, but that space that's been contracted, does that just like reset?
Yeah,
So
because
does it just so you've if does
it
it reset so then
relaxes.
you've technically not moved?
Whatever's inside, if you switches off, whatever's inside just suddenly stops moving wherever you are, and the deformation, expansion, and contraction just uh, drops down to flat space. Eventually, it senses gravitational waves and it relaxes to flat space again, which is what you
Okay,
had before. So
so all we need to do is drop the bubble, hop on one of the gravitational waves, and ride the wave away from the region of space before it expands back out. There we go. I've solved it. I've
yeah.
solved it.